So in this video, we are going to look at more examples for constructing NFAs. In fact, we'll look at more involved problems. Okay, in this question, we are asked to design an NFA which will accept all the binary strings whose fourth symbol from the left is 1. Okay, let's look at some examples now. So if you look at this DF, this string, you can see that this is the, so you should identify left and right. This is your left side and this is your right side. Given a binary string, this is going to be your left side and this is going to be your right side. So when I say fourth symbol from the left is 1, so if you look at these symbols, this is the first symbol, second symbol, third symbol, and fourth symbol. So here we can see that the fourth symbol from the left is a 1. So this string has to be accepted by your NFA. And similarly, look at here. So this is, so when you look at this string also has a fourth string of 1. So this has to be accepted. Similarly, this also has your fourth string as 1. And hence this string also has to be accepted. But look at this string. This string has the fourth string. This string has the fourth string as 0. So this string should not be accepted. So our NFA should be designed in such a way that it will accept all the strings whose fourth symbol from the left is 1. So let's start designing it. So it means that when so if you're getting, you can start at Q0, and so you're not actually worried about 0 or a 1 as long as you reach the fourth symbol. So this is your first symbol. It can be either a 0 or a 1. And now this is going to be your second symbol. It can also be either 0 or 1. Now you can go to the third symbol. This also can be either a 0 or a 1. Okay, so up to that, it's okay. Now the fourth symbol has to be exactly 1, right? So the fourth symbol has to be 1. So we'll make a transition from Q3 to Q4 only upon saying a 1. And from there you can have so once you are reached here, you're not actually worried about subsequent symbols. So you can put a loop there saying 0, 1. Now you can see that this NFA will accept 0 or a 1 for the first 3 cases. For example, here the first alphabet can be 0 or a 1. Second alphabet also can be a 0 or a 1. The third alphabet can also be a 0 or a 1. But the fourth alphabet has to be a 1. So if you get a 0 here, if you get a 0 here, that means if you are getting a string like this, okay, so it will reach up to Q3. From Q3, it will be going to a dead state. So this NFA will accept all the strings whose fourth symbol from the left is a 1. So we have another question here in which we want the third symbol from the right. Third symbol from the right as 0. So remember, this is asking for the third symbol from the right. So you know that if you are given with a string, so suppose the string given to us is 0, 0, 1, 0, 0, 1, 0. So if you look at the right side, the first symbol is 0, the second symbol is a 1, and the third symbol is a 0. So these types of strings, so if you have the third symbol as 0, this has to be accepted. So if the third symbol is a 1, then it should not be accepted. So we have to design such a DFA. So we can actually design this in the reverse way. So we can actually write the final state initially, and then go in a reverse way, and then we can actually do it very easily. So suppose this is going to be my final state. I'm not going to number the final state now. So the last symbol that you see can be anything. It can be a 0 or a 1, right? And the second last symbol can also be anything. There is no restriction on that. So from here, you can have anything. Okay, so it can be 0 or a 1. And the third symbol, there is a restriction. So you have a restriction on the third symbol. So that's going to appear here. Okay. So the third symbol has to be a 0. That's a restriction. So we have actually added the restriction. And now the starting can be anything. Okay, so initially the start from if you look from the starting state, you can get any kind of symbols, 0 or 1. That doesn't actually matter. So yeah, the only thing is that once you start seeing a 0, okay, once you start seeing the third symbol from the right as a 0, then that string should be accepted. So let's give some naming to this. So let's say it is Q0, Q1, Q2, Q2. This is going to be Q2, and this is going to be our final state, Q3. So if you carefully look at this this NFA, the last alphabet will be anything. That's the rightmost alphabet. That's the first alphabet from the right. So this is our first alphabet from the right. This is our second alphabet from the right. This is going to be our third symbol. Okay, third symbol from the right. So alphabet and symbol both refers to the same. So the third symbol from the right has to be a 0. Okay, and initially you can see any type of symbol, 0 or 1, right? So this will accept all the strings having the third symbol from the right as 0. So in this question, we are asked to design an NFA which will accept binary strings. So remember, the strings are binary in nature. Okay, so which will contain exactly 2 ones, right? So we are interested in counting only ones. Okay, so let's start drawing it. So this is going to be my initial state, and from there, if you see zeros, so I'm not interested in seeing zeros. So whenever I get a 1, I move to the next state. Okay, from there again from Q1 you can start, you can get anything, right? So you can start any number of zeros, right? So I'm not interested in counting zeros, and if I get a 1, I will go to the next state, and then I will make that as my final state, right? Now from here, from Q3, you can have any number of zeros, but you cannot have ones. Okay, so this is going to be our NFA. So if you give any string which contains exactly 2 ones, this DFA will accept. There is a path through which that string can be accepted by this NFA, right? So remember, we have already designed these types of DFAs earlier, and you can see that how simple the NFA is compared to the DFA here. Okay. So we have a slightly more tricky question here. So we are asked to design an NFA to accept at most 2 ones, binary strings having at most 2 ones. So whenever you hear the word at most, it actually refers in this question, it refers that you can see no ones at all. So 0 ones. So if you see no ones, that's also acceptable. If you see 1 that's also acceptable. If you see 2 ones, that's acceptable, right? So but if you see 3 ones, this is not acceptable, right? So we have to design our NFA in such a way that it can accept strings without any ones, with 1 okay, with even with 2 ones, but not with 3 ones. Okay, 3 or more than 3 should not be accepted, right? So let's start designing now. Let's say our Q0 is our starting state. Okay, the Q0 itself becomes the final state. Okay, and the transition to Q0 is on 0, right? So this means that till here you don't have seen any ones. Okay, so no ones are seen. So that also has to be accepted, right? And now let's make a move to Q1 upon seeing a 1, and that also has to be a final state, right? Because 1 has to be accepted. Okay, now you can have any number of zeros, and from there if you see again a 1, this also has to be. So it means that whenever you are at Q2, you have seen 2 ones, exactly 2 ones. So that also has to be accepted. And from here you can keep on seeing any number of zeros. But if you start seeing a 1 from here, then it should not be accepted, right? So suppose we'll look at an example. So suppose our string is 0, 0, 1, 0, 1, 0, 1. Okay. So what will happen? Let's go through this. So the pattern here is 0, 0, 1, 0, 1, 0, 1. So let me trace the pattern here. So when you get a 0, first 0, you'll be here. Again a 0, you'll be here. Again you're seeing a 1, you'll be at Q1. So you have seen 1, 1, right? And then you're seeing again a 0, so you'll be at Q1 itself. Then you're seeing one more 1. Okay. So now you are at you are at Q2. Okay, and then from there you are seeing one more 1. Okay, so from Q2 you are seeing one more 1, and the problem here is that the transition for Q2 on 1 is not defined. So this string will not be accepted, right? Because it contains 3 1s, and from Q2 I don't know. If I'm getting a 1, I don't know where to go. So if such a situation occurs, we already seen that if you don't know where to go, it is a dead state. You are at a dead state, right? So even though you are at Q2 in the previous step, means after seeing 2 1s, you are at Q2, and then you're seeing one more 1, then that means you are actually at a dead state. Okay, so when you see one more 1, then you're actually at a dead state, and so this string should not be accepted. Okay. So suppose the string was only up to here. So this one is not there. Then this would have been got accepted. So we have another question here, which actually wants us to. So we have another question here, which actually wants us to accept or to construct an NFA to accept binary strings containing at least 2 1s. So the wording is different here, at least. In the earlier question, it was at most. So we should, in the earlier question, we should see maximum 2 1s. Okay. And here, the condition here is that you should have at least 2 1s. So you should not accept strings like 0, 0, 0, or 0, 1, 0. So all these types of strings should not be accepted, right? So let's start building the NFA. So let's start at Q0. Okay. So as long as you see 0, you can stay at Q0, and when you see a 1, you can make a move to Q1, and from there again, if you see zeros only, you can stay there. From Q1, if you see again a 1, you can move to Q2. Okay, so in this NFA, if you have reached Q2, it means that you have seen 2 1s. Okay, definitely you might have seen 2 1s once you reach Q2. Okay, so from Q2 you actually not bothered about seeing any number of 1s or zeros. So you can have a transition on 0, 1. So this means that after I have seen 2 1s. Okay, I have seen 2 1s. I can see any number of zeros or 1s. That's not an issue. So let's look at an example here. So suppose my string is 0, 1, 1, 0. Okay, 0, 0, 1. So this is a valid string, even though it contains three 1s. So this particular string contains 3 1s, right? 3 1s are present, and we need only at least 2 1s. So this string has to be accepted. So let's go through this. So once if let's trace the string and understand this. So I have 0, 1, 1. So when I get 0, I'll be here, again a 1 here at Q1. From there, again, I'm getting a 1, so I'll be at Q2. From there, I'm getting 3 zeros. So 0 transition is defined here. So all the 3 times it will come back to Q2. And lastly, I have a 1, and the transition is also defined here. So I'll be at Q2. So I will not go to any dead state. I will be at Q2 itself. So this string is said to be accepted, right? This string is set to be accepted. Now, an interesting thing to note here is that the NFA that we have designed contains transitions for 0 and 1 in every state. So if you look at Q0, you have transitions. You have transitions for 0 and 1. If you are at Q1, you have transitions for 0 and 1. Similarly, Q2 also has transitions for 0 and 1. So this NFA that we have designed is actually a DFA. Okay, so when you design NFAs and if you end up in getting DFAs, that's also perfectly valid, right? So you start to design NFAs and then you are ending up at DFAs, right? So that's very much okay, because we have seen that every DFA is an NFA, right? But every NFA is not a DFA, right? So since every DFA is an NFA, it is not an issue if you are getting, while solving the problems, if you are getting a DFA as an answer. I mean, that's perfectly okay. Now let us look at some questions involving word size. Okay, so all these questions are defined on binary strings. So the alphabet set here is again going to be 0, 1. Okay, so we are asked to design NFA which will accept all binary strings whose word size is going to be less than or equal to 3. Okay, so let Q0 be the starting state. From there, I can either see a 0 or a 1 and move to Q1. So if I am at Q1, it means that I have seen one symbol. And if I see again another symbol, I will be at Q2. So again on 0 or 1, I can be at Q3, right? So if I am reaching Q3, it means that I have seen 3 symbols. So this NFA will accept all binary strings whose word size is exactly 3. If this is the way I draw it. Okay, so it will look for the first symbol, second symbol, and third symbol. So once it has found 3 symbols, okay, then this is a perfect NFA for accepting whose word size is 3. So the next question is we have already solved the next question. That is, this word size is exactly 3. But this particular question, we are asked to design whose word size is less than or equal to 3. So it is quite possible for us to have the size 0. So Q0 has to be your final state for accepting strings with size 0. You can also accept strings with size 1. So Q1 also has to be a final state. And similarly, Q2 also has to be a final state, because we can also accept strings with size of 2. And Q3 obviously is going to be a final state, because we are going to accept strings with size 3. And it's very important that you should not provide any transitions from Q3. So if you provide any transition, then it will make it will accept words having size more than 3, right? So this is going to be the end of it. So the word size 3 is very trivial. We have already seen. We can actually draw it. Okay, so Q0, from Q0 we can have Q1 upon seeing a 0 or a 1. From Q1 you can have 0, 1. On 0, 1 you can go to Q2, and from there again 0, 1 you can go to Q3, and then you can stop there. Okay, so in this case Q3 is the only final state that you're having. Okay, in the previous case all the states were final states, just because we wanted the word size to be less than or equal to 3. But here in this question we want the word size to be exactly equal to 3. So that's why we have only Q3 as a final state here. Okay, so we have one more question, which asks us to have the word size greater than or equal to 3. So for word size greater than or equal to 3, we can actually modify the word size which is equal to 3, which this NFA can be modified. The only thing that you need to do here is to provide an additional transition from Q3 like this. So you can have anything 0 or a 1 there, so that it will accept strings whose word size is greater than or equal to 3. So we expect minimum of 3. Okay, let me erase this and and draw the NFA. So this is going to be very easy. We can actually modify the previous NFA like this. So you start at Q0, and upon seeing a 0 or a 1, you are at Q1. Again, upon seeing again 0 or a 1, you're at Q2. And from there, if you see again a 0 or a 1, you're at Q3. And since the question is about word size greater than or equal to 3, we should give a transition on 0 and 1 here, right? So minimum we expect three symbols. Okay, so this is the NFA for accepting binary strings whose word size is greater than or equal to 3. Okay. Okay, now let's move to the assignment section on more problems on NFA construction, right? So the first question is, you need to have your fifth symbol from the right as a B. And remember, here the alphabet set is A, B. The second question is to accept, construct an NFA to accept binary strings with a word size 0 mod 3. And similarly, the third question is to accept binary strings with a word size 2 mod 3. So these two questions corresponds to modulo arithmetic notations. So we had a very detailed video on how to solve problems with regard to modulo arithmetic notations in DFA. And a very similar approach can be used here. Okay. And again, remember, in the process of designing an NFA, if you're getting a DFA, that's also perfectly okay. Now the last question here is to design an NFA for accepting binary strings with the specification of this word size. So it tells you that the word size has to be greater than or equal to 3, but it has to be less than or equal to 6, right? So you have to construct an NFA for that. Okay. And remember, you can submit all these assignments in Moodle, where it is mentioned that the question is for assignment set 1 on NFA construction.